Newton's second law is a law that we've learned in physics. It's extremely important to our studies. And we've already learned Newton's laws, or two different versions of Newton's second law. And so now we're going to learn a third version. So let's review first, looking at those first two versions that we've learned. When we first learned Newton's second law, we learned it in a pretty standard format as we were learning all three of Newton's laws. The second law we learned was that the net force equals mass times acceleration. We've used that equation a whole bunch. As a matter of fact, it's probably one of the few equations that you may have memorized from physics so far. Then fast forward a couple of units, and we learned a second version for Newton's second law that said that the force was equal to the derivative of momentum with respect to time. We actually talked about how this was the original way that Newton wrote his second law. Well, now since we're focusing on rotation, we're going to look back at that first version, but think of it in terms of rotation rather than in terms of linear or translational motion. So instead of net force, we're going to think about the rotational equivalent of force, which we know is torque. Instead of mass, we're going to think about that rotational equivalent of mass, which we've learned is moment of inertia. And instead of a linear or translational acceleration, we're going to use a rotational acceleration. So our equation here is that the net torque equals the moment of inertia times that angular acceleration. This equation will come in handy in several instances. One example of a time that we'll use this equation will be when we have pulleys, because now, as opposed to what we've studied before, we can handle pulleys that are not massless and frictionless. So we'll see examples with that, and we'll also look at examples of several other things that are rotating and apply this equation to those examples. Commonly, after we study Newton's second law, we also talk about something called equilibrium. And in the past, when something was in equilibrium, it meant that the net force was equal to zero. So our object is either at rest or moving at a constant velocity, and all the forces add up to being zero. Now, since we're thinking about things not only moving linearly, but also rotating, we're adding an extra requirement to something being in equilibrium. Now, when something is in equilibrium, both the net force and the net torque must be equal to zero. This is going to be really crucial in analyzing equilibrium problems because it gives us another tool in our tool belt when we have too many forces that are unknowns. So one thing that's really common in equilibrium problems when we're looking at the net torque being zero is we have the opportunity to set the axis of rotation wherever we would like it to be. So typically we'll set that axis of rotation to be at a point where there is an unknown force, so that the torque from that unknown force is equal to zero, since the radius would be zero. That'll allow us to have only one unknown in our equation and solve for an unknown force. We'll see several example problems showing exactly how to use these two conditions for equilibrium.